So we are going to start the last talk of today. It's my pleasure to introduce Chao Li from Stanford University. He's going to talk about index, wait a second.
Index and topology.
Index and topology of minimal hypersurface in RM. Thank you.
Thanks for letting me have the chance to speak here. Before I start, I should say that I'm not a native speaker of English, and I do not claim myself to be an expert in minimal surface theory either. So if you recognize any questions or comments or you want to discuss something, please don't hesitate to ask. So today the topic I'm going to speak on is about index and topology of minimal hypersurfaces in Rn, Euclidean space. So our object to consider today is n-1 dimensional minimal hypersurface contained in Rn, and we always assume such a surface as a complete and two-sided, meaning that it has a globally defined unit normal vector field. So before I went into any detail, let's first fix some definitions. So minimal surfaces are the critical point of the area functional, and we can talk about the second variation. And for a two-sided complete surface, the second variation can be given by a quadratic form. It is denoted by QFF equals to the negative of the integral FLF, where F here represents a normal variation. And L is the Jacobi operator defined by Laplacian plus the square of the second fundamental form norm. Okay, and now with these notations, we can define the Morse index of a compact subset of sigma to be, let's say it's intersect any ambient ball of radius r, to be the number of negative eigenfunctions or eigenvalues, let's say, of the Jacobi operator with the Dirichlet boundary condition. And for a complete surface, we define the index to be the limit of a compact exhaustion. So okay, so by the basic spectral theory, such a limit always exists, and it might be infinity. Okay, so as you see, index is a notion naturally coming from the variation with an analytic theory of minimal surfaces, hypersurfaces. Then as geometer, we naturally want to relate this notion with the geometric or topological invariance of the surface. Right? So a natural question to ask is to characterize the topology of a minimal hypersurface of given index. Okay, so towards that end, we have many classical works in the development of the theory. For example, the most fundamental one maybe is due to Fisher-Coburey, and shown in 80 and independently by Docamo Peng in 79, and also independent by Pogarello in 81, which says that if you have a two-dimensional surface in R3 and it is stable, stable means index is 0, then it has to be the plane. Okay, so back to the time this theorem was proved, the plane and the catenoid and the helicoid were the only minimal surfaces known to people. And also, but back then there's not so much research going on for positive index minimal surfaces until new examples were discovered by Costa, Huffman, Mix. So I want to mention a little bit of non-trivial examples of minimal surfaces and how its geometry and topology related to the Morse index of them. So let's look at some examples. So the first example I want to discuss is, of course, the Costa surface. Discovered in 94. So this surface can be viewed as a desynclarization of the union of a catenoid with a plane. So if you just put together the catenoid and the plane, it's basically a minimal surface, but except for their intersection. On their intersection, there's a singular S1. Right? So there's a way to desingularize this surface by putting a handle inside. Therefore, the surface you get is it's basically still a catenoid union with a plane, but with one handle inside. Okay, so this way you get a non-trivial embedded minimal surface, and of course you see there's one handle inside, so with the genus is 1, right? And there are 3 ends. End means that outside a compact set, how many components you have. So for this surface, you see the catenoid has 2 ends and the plane has 1. So the end, we denoted by R, is 3. Right? So, and later, it was proved by Natayami and that the index of such a surface is going to be 5. I'm sorry, 5. Okay. All right, let's look at some more examples before going on to the theory. In fact, the desynclarization of the union of catenoid and the plane can be done in many ways. In particular, you can put more than one handle in their intersection area to get a genus G Costa surface. So you can put a bunch of handles inside, basically. So for every integer G, you have a genus G Costa surface. And still it has 3 ends. And the stability property of such a surface has also been studied by conformal method, and it was proved by Natayami and later by Morabito, 2 Japanese mathematicians, that such a genus G Costa surface has index 2G plus 3. Okay. Right, so the Costa surface is one large collection of embedded examples. And if you are willing to sacrifice the embeddedness a little bit, so we have a George mixed surfaces. So this family of surfaces are always simply connected, but it has more than 2 ends. So let me say with R ends, where R is at least 3. So the surface looks like the following. You take one, you basically construct a polygon, and on each of the vertices of the polygon, you somehow attach a catenoidal end, let's say. Okay, so for example, what I draw here is a George mixed surface with 3 ends. Right? So each end here is, you may imagine, it's asymptotically a catenoid. So it will have self-intersection, right? Near each of the 3 parts, it has self-intersection. And you can do the same thing for arbitrarily many n, right? So any choice of r, at least 3, you can do the same thing. And it was proved by Van Til and Ross that the index of a George mixed surface with Rn is actually 2r minus 1. Okay. Yet, and the proof is also a conformal method. You basically look at the Gauss map of such a surface, and basically singularity of the Gauss map lie on the equatorial circle. Then you can use some reflection principles and so on to prove the index is 2r minus 1. Right? So these 2 examples indicate a pattern that the index of the minimal surface in general increases as you put more genus or more ends onto that. Right? So there are many researchers going on studying the genus and number of ends and this relationship between with the Morse index of the surface. Due to the time limit, I will only write down one of the most conclusive results here by Otis and Davy in their recent paper. They can prove that for a 2-dimensional surface contained in R3, let's say an immersed surface, then the Morse index is at least a linear function depending on G and R. Okay. This result is quite a good result. For example, it tells us that for 2-dimensional surfaces, we know that the genus and the number of ends uniquely determines, for example, the diffeomorphic type of the surface. So this theorem implies, in particular, that for a given index, there are only finitely many diffeomorphism types of minimal surfaces with that index, right? With that index upper bound. So, yeah, these 2 results are both very nice, but they have one thing in common, is that they are all about 2-dimensional surfaces in R3. So the question is natural: what happened to higher dimensional surfaces, right? So, of course, people have studied the higher dimensional analog of the first question. Can you say anything about a stable hypersurface of, say, R4, for example? Right? That question turns out to be quite hard and still open till now, but we do have one result towards that question that is due to Chao, Shen, and Zhu, 3 Chinese mathematicians. In 1997, they managed to prove that if you have a minimal hypersurface in higher dimensional Euclidean spaces, then if the stable, it can only have one end. So such a statement is still far from being, far from that concluding sigma is the plane, but still we know something. And what about the positive index case? Well, that question is more difficult because, for one thing, we don't know any explicit example such as Costa surfaces or George mixed surfaces to begin with, but nevertheless, it was proved by Peter Li and Jiaping Wang in 2002 that if you have a higher dimensional minimal hypersurface with finite index, then they can conclude that the number of ends is also finite. So this is a qualitative statement, right? So there's no quantitative relationship between the index and the number of ends, right? So what we can prove today can be viewed as a quantitative generalization of Li Wang's result. So what we can say is that with one additional assumption that this minimal hypersurface has finite total curvature, then the index plus the nullity is bounded from below by a linear function of the number of n's plus the first better number, where here nullity is the dimension of L2 solutions to Jacobi operator. And this holds for all dimensions. Now, of course, the nullity term here turns out to be quite subtle in many technical applications of such an estimate. So, of course, I tried very hard to eliminate this nullity term in the inequality. But I can only do that for now in one case. That is when the dimension is 4 precisely, when n is 4 precisely. So if you have a three-dimensional surface, hypersurface in R4, and with this low dimension, we can slightly loosen the condition to be that the sigma has Euclidean volume growth. Then the index is bounded from below by a linear function of the number of n's plus the first better number, but with a slightly worse constant. Okay, right, before talking about the proof, which might seem not so interesting to many of you, maybe, let me first make some remarks and some applications of such an index estimate. So let me write down here. So for the surfaces we consider, namely in general it has finite total curvature, or in low dimensions it has Euclidean volume growth. These surfaces has the property that, let's say, sigma n minus 1 contained in Rn has either it has finite total curvature, or for n from 4 to 7, that's Euclidean volume growth. If one of these two conditions hold, then we can conclude that the end, each end of such a surface is a planar end. It's so-called regular at infinity. Then sigma is the notions regular at infinity, which I'll not explain in detail, but you may think about that each end of the surface is approximately a plane, basically. So the number of ends corresponds to how many infinite planes this surface have, right? So in other words, there's a geometric interpretation of the number of ends. That is, the number of ends of sigma is going to be the density at infinity of the surface, right? So our theorem basically says that under some proper conditions, we can use the Morse index to bound the density at infinity. Well, such a bound proves to be very useful because once you know such a bound and combine a recent work of, so let me write it as the first application. So if you combine our result with the recent work of Katover todos and maximal, we can immediately see the following analog of the two-dimensional picture we have in mind. That is, for there exists an n depending only on the index, such that the set sigma 3 contained in R4, sigma has Euclidean volume growth, and index is bounded by I, has only finite many diffeomorphic types. So a density bound at infinity directly gives you this result. And it can be proved by a compactness argument, basically. Once you know a uniform bound at infinity, you can run a compactness argument to prove such a finite diffeomorphism type theorem. And another application, actually I find also a pretty interesting one, is lies in the same spirit of the first application. So it is another interesting question related to characterizing the stable surfaces, right? So the next simple example of minimal surfaces, apart from stable ones, are index 1, right? So the question is, what are index 1 surfaces? And so this question seems to be not so hard, but okay. So in 2 dimensions, it is proved by Rouse that if you have a 2-dimensional surface contained in R3, and it has index 1, and it's oriented, then sigma can only be the catenoid or the anapur surface. So in particular, if you allow, if you say sigma has finite total curvature, then it is catenoid, right? So index 1 surfaces are expected to be quite unique, right? So they are catenoid, basically. And what about higher dimensions? Can you say anything about higher dimensional index 1 hypersurfaces of Rn? Well, ideally, we want to prove it's a higher dimensional catenoid, right? But I cannot do that. Instead, I have another characterization of index 1 surfaces, namely the following. So what I can say is that there exists a uniform constant R bigger than 0, such that the following is true, such that if sigma 3 contained in R4 has Euclidean volume growth, and index 1, and also normalized, let's say normalized such that the maximum of the curvature is achieved at 0. Then outside of the ambient bow of this given radius R, the surface has to be a union of minimal graphs. So in other words, any topology, if it happens at all, must happen inside this big bow R. Note that this R is a universal constant. So one can study actually a perturbed, deformed family of Costa surfaces. And if you do that, it's very easy that you can see such a statement cannot be true if you allow this index, if you change the index 1 to some other number, to 5, say it's not true then.
Does Euclidean volume growth be quadratic?
Well, it's a three-dimensional surface, so it's cubic. Yeah. Right. So, so maybe this corollary can be viewed as an evidence that somehow the catenoid is still the unique minimal hypersurface with index 1 and Euclidean volume growth. Okay. Let's, how many time do we have? 4 minutes. 40. 14. Okay.
You have 10 minutes.
10 minutes. Right. Yeah, 10 minutes. Then let's talk about the proof of these index estimates. I find one difficulty that about minimal surface theory is that the two-dimensional theory is heavily depending on the conformal technique somehow. But conformal technique cannot be generalized to higher dimensions. So the proof of the index estimate is actually pretty different. If you look at the proof, it's a pretty different flavor of previous ones. But nevertheless, the basic idea comes from an old observation from Shen Yao. So what they can say is that if you have a stable minimal surface, hypersurface, regardless of the dimension, then it cannot carry any harmonic one form, L2 harmonic one form on that surface, basically. Well, okay. So the study of higher dimensional surfaces, minimal hypersurfaces, has used this observation many times. And in the proof of this theorem, we also consider, in the first step, we also consider the space of L2 harmonic one forms. L2 harmonic one forms on sigma. And without much difficulty, we can say that, let's denote the space by H. Then we can prove the dimension of H is at least the number of n's plus first beta number minus 1. Okay, so that's the crucial number appeared in the theorem. Okay, so once we have this, we're going to use a sort of a miraculous formula discovered by, suggested actually by Alessandro Salvo. So we consider such test functions for each pair of integers I, j. We consider this function depending on a harmonic one form, and also let's say omega is a harmonic, L2 harmonic one form, and indices I and j defined to be di tangent part paired with omega, dj nu minus dj tangent part omega di nu. Okay, so let me mention that such test functions has also been used by Professor Luke Ambrosio and Ben Sharp and Alessandro to study the Morse index of compact surfaces and surfaces with free boundary condition. Whereas in our complete case, there's a little bit more subtlety. So once we have these functions, there's a technical lemma, a sort of lengthy calculation, but this is where the miracle happens, is that if you sum up all these functions, multiply the Jacobi operator acting on that, you get 0. Okay, then we apply the Hirsch trick. So what we do is that pick out all the negative eigenfunctions then consider the linear system namely you want the test function to be L2 orthogonal to each of them. Okay, so, and this holds true for every pair I and J. So you see, if you count the number of equations inside this linear system, then on every line here, it has I equations. But you want to run over all the pairs I and J, so the total number of equations equals to I times n choose 2, basically. Right? So therefore, if the dimension of our if the dimension of H is bigger than this number, then we can find a solution, right? So it's a linear algebra thing. We can find a solution to this linear system such that the equation star holds, right? Therefore, by variation theory, if you consider this variation given by f omega ij, it should be non-negative, right? By the definition of Moore's index. But on the other hand, by this calculation lemma, if you sum up all the pairs I and J, you get 0. So in particular, every single one of them should be 0, or should be in the kernel of the Jacobi operator. Right. So that way we produce a lot of Jacobi functions, namely, if the index is small, then the nullity must be very huge. And basically, their sum should be, I'm sorry, I just erased this. So in theorem 1, it says that the sum of index and nullity is bounded from below by this dimension, right? So that's the rough idea of proving theorem 1. And for theorem 2, we need to be more careful. So for theorem 2, it involves the third step, meaning that we need to look at when such a thing happened, right? So the Jacobi operator acting on f omega ij is 0 for all pairs I and j. This is not a condition that is likely to hold. So what is true is that locally you write omega as a differential of harmonic function where Laplacian phi is 0. Then this above condition means that the Hessian of this function and the shape operator commute. Okay. So it's a very overdetermined linear system. And we're able to bound the solution of such things when the surface is not in some way homogeneous. So there's a geometric proposition which we can say is that if sigma has one point where principal curvatures are distinct, then the dimension of such things harmonic function whose Hessian commute with the shape operator is at most 2 times n minus 1. So namely, such bad situation can only happen for at most this number of functions. Therefore, the index estimate should hold true in general. And there's another proposition we can prove to guarantee that for when n is 4, this condition basically always holds. And in general, we have the following thing. So if for every point on the surface, there are n minus 2 equal principal curvatures, then sigma can only be the plane or the higher dimensional catenoid. Where we know the index explicitly. So I think that's all I want to talk today.